Hi everybody, in this video we're going to take a look at modeling some data from Norman Bowen's 1913 study of plagioclase solid solution. These are a series of experiments that were conducted at a range of temperatures that are shown over here in this column, and he used as starting materials a single plagioclase feldspar that he would melt, or a single plagioclase liquid composition that he would crystallize, but varying in composition between pure anorthite here at 1553. So if you get pure anorthite, it would melt at 1553 degrees centigrade, and pure albite, which melts at 1118 degrees centigrade. And then these intermediate temperatures, he would take compositions that are a mixture of albite and anorthite and melt those. And in other videos, we talk about solid solution, so you can refer back to those videos to understand how solid solution works. Here, we're going to focus on the modeling of this data. So this is data that's just pulled directly out of his tables from that 1913 study. And we're going to write a couple of equilibrium constants, and we're going to plot them. So for the equilibrium constant for albite, we can write it as a crystallization equilibria. So I've written that here, where we have NaAlSi 308 in the liquid goes to the same compound in the solid. So we're precipitating out an albite component. Because we are writing albite here, that does not mean that there's no anorthite in the system. We're just isolating the albite component that is in the liquid. And the only time that we would have pure albite would be the case of this temperature, this experiment here, where Norman Bowen used pure albite in the experiment. So the equilibrium constant would be products over reactants. So we're writing this as a crystallization equilibrium. We'll have albite divided by albite in the solid divided by albite in the liquid. For the pure anorthite case, that just gives us a bunch of nonsense. So we'll get rid of that in a moment. We don't need that value, but as we fill down, we can get these values down here. And I've set it up so it plots over here. In this diagram, we're plotting the equilibrium constant versus temperature. Now, for these data, we can fit this through, let's go to trendlined options. Oh, it's unhappy with choosing, there we go. We can fit it pretty nicely. Let's move this over so we can see it. It's fitting a linear. That doesn't do a very good job, but we could try a polynomial. You can see it fits a little bit nicer. And we could make it a third order or a fourth order, and we could fit the data really, really well. Let's display the equation on the chart, and you can see that we are explaining about 99% of the variation, actually almost 100%. Let's increase this a little bit. So what is our y? Our y is what's on the vertical axis. It's the equilibrium constant for albite. And everywhere you see an x, that's our temperature in degrees centigrade. So we've got a fourth order polynomial here, and we can describe this variation in the equilibrium constant as a function of 4 times 10 to the 11 times t to the fourth power minus 2 times 10 to the minus 7 t to the third power, etc. When you see this 4e, that means basically 4 times 10 to the minus 11. And this is minus 2 times 10 to the minus 7, etc. The problem with this equation, though, is even though it gets this really beautiful fit, this equation has no theoretical meaning. This is an empirical model. It means it's based on observation. What we want to use is a theoretical model, which will actually give us something not only that we can interpret, but also a little more simple of an equation to fit. And we're going to use this theoretical model here. We're going to use this equation, minus RTlnK equals delta G. Delta G can be expanded to delta H minus T delta S. And we're going to linearize this problem by essentially rearranging this to solve for the natural log of the KEQ. So we want the natural log of the K. In this case, it's the K of albite. And we can write this out as lnk equals minus delta H divided by RT, so lnk is equal to minus, I'll just write as a dH divided by RT, and then plus ds divided by RT. So we're dividing everything. Oh, we're going to lose the t because this t is going to cancel out. So we get this equation here, and what we're doing is we're linearizing the problem. The lnk, the natural log of the equilibrium constant, that will be our new y value. So I'll take the natural log of this, which is meaningless, but I'm just going to do that for completion and then fill down. We'll just delete that value because it doesn't do us any good. And notice that our y here is effectively a 1 over t. So when we solve for lnk, we get minus delta h over r as our slope, and delta s over r is our b value, our y-intercept. So this is y is equal to mx. What's the x? It's a 1 over t. So we want 1 over t here. And because we want to derive values for delta H and delta S, we're going to use the gas constant. The gas constant is given in kelvins. So we're not just going to take 1 over T, but 1 over the temperature plus 273 to convert that to kelvins, and then we will fill down. So I want to chart both of these. I'm going to drag this over to the right-hand side, because I want to just be able to grab these values and copy and create a new chart. I'm going to get rid of this stuff here. And we'll go to Edit, Paste Special, Values. And I need to change the axes here. And I'm going to have to change the way I have formatted them. So we want to go down to 0 and a maximum of 0.0008 will probably work. And then for the natural log, we're going from a minimum of minus 1.1 up to, we can go to 0. So now take a look at the chart. We're charting negative values. This is no longer just the equilibrium constant, but rather the natural log of all of that. And this is 1 over t, and we'll specify that we've given this in Kelvin. What we've done is we've linearized the problem. I'm going to get rid of some of this extra empty space. So the minimum that we need is, a better minimum would be 0.005, I think will work. And notice now that, again, that curve is turned into a straight line because we've taken this equation here, and what we've done in effect is we've linearized the problem. We're not going to get a perfect fit, but we can now take these data and we can fit a line, and we'll double click on this line so we can display the equation on the chart and also the r squared. We've got a pretty good fit. We're just explaining about 99.8% of the variation. And the beauty of this is not only can we do linear modeling, but these values now have some theoretical meaning. So this is the natural log of the k of Albite, and that is a function of 1 over temperature. So I'll just write this as that. And if we take a look at this equation and compare it to what we wrote here, our slope, m, is equal to 6751.9, and our b value, our intercept, is minus 4.8693. Now, we can compare this to this equation here, our value of 6751.9. That's our slope. That is equal to minus delta H over R. So this is so if we simply take, so if this is equal to minus dH over R, oh, it thinks I want to write an equation. I don't want to do that. Let's put that in quotes and see if that helps Excel understand what we're trying to do. So if this whole thing, 6751.9 is minus dH over R, we can calculate the delta H by simply taking the slope and multiplying it by the value R. And by the same token, if this is equal to ds over R, then we can calculate the delta S by simply taking the slope and multiplying it by the value of R. And did I lose a minus sign? No. Right. Oh, yes, I did. So we have a minus value out here. So we need to put a minus value over here. So the delta H has this value. Now, what are these units? The lnk, the natural log of k, should be unitless. And we're multiplying this by R, which I've written out in joules per mole dot K. The only way that this term here, the dH over RT, can be unitless is if the dH is in joules per mole. So this would be joules per mole. And the only, not an N, but an M. And the only way the delta S can cancel out all its units is if it has the same units of R, which is mole star K. So these are the units that we get. We usually write delta H in kilojoules per mole. So if we divide this by 1,000, then we get this in units of kilojoules per mole. You can work this out with pen and paper. You probably should. Play with this equation to prove to yourself that this is in the form y is equal to mx plus b when we plot lnk versus 1 over t, and that the units here cancel as they should, so that the lnk is unitless when you're all done with the calculations. Anyway, the key issue here is that if we kept the curve and fitted a polynomial, we get a bunch of coefficients that are meaningless. But by linearizing the equation and applying a theory to get that linear model, we not only get a simpler interpretation and an easier kind of regression that we can work with, but we can get a model that we can extrapolate outside the range of calibration, which you cannot do with the fourth order polynomial that we looked at earlier. Plus, the coefficients that we get now have meaning. This delta H is the heat of reaction for crystallization. It's giving us the amount of energy that's released, 56 kilojoules per mole, when liquid is precipitated out as solid. And it also gives us the entropy change of that. So we have coefficients that now have theoretical meaning that we can also test by doing other kinds of experiments. And then again, as always, by linearizing the problem, we get a simpler regression model that's going to be a little bit more trustworthy.